So, if you want to be a seismologist, then you will have to study seismology, which essentially is the study of earthquakes and earthquake waves. Now, you might get different variations as a multiple choice type item. They could say things like, that studies the movement of waves through Earth, for example, but it will all come back to studying earthquakes, seismic waves, earthquake waves. That is the study of seismology. Now, if you are a seismologist, then you will work at a seismograph station, and seismographs are basically instruments that measure seismic waves. Seismographs can be vertical and horizontal. I imagine that there are improvements in seismographs now with the just with technology in general. I will show you a diagram, however, of an old vertical seismograph, so you can see just essentially how they worked in the past. It is at seismograph stations that you get printed records that are created by the seismographs, and they're called seismograms. So here you have a picture of a seismogram, which is a printed record that you actually get from an earthquake that occurred and recorded at a particular seismograph station. These kind of remind me of like heart rate monitors. With a heart rate monitor, you do not want to see a flat line because it means that the heart has no electrical activity and the person is probably dead. Whereas with earthquakes, flat lines are good. It means that there's no earthquakes occurring, and as a result, there's no risk to human safety. In this particular printout, as we can see, there was an earthquake, and in this vicinity right here, nothing was taking place. And then all of a sudden, this is the arrival of the first P wave. So it's about right there where the P wave actually arrives. And the P wave passes through. And then you wait for a certain amount of time. And the question is, how long do you have to wait? The longer you have to wait, it means the further away you are, your station is from the earthquake. The S wave arrives right here. So this is the P, and this is the S. The S wave comes through, and then after a while, your surface waves come through. Now remember, surface waves travel along the surface of the Earth, so they will be last to arrive at a station. Whereas P waves and S waves are body waves, they can actually go through the body of the Earth, with the exception being that S waves cannot go through the liquid outer core. So in every seismogram, well, not every seismogram, you don't get all three types of waves in all three in all seismograms, and we'll explain that in a later video. But for the most in most cases, you will get all three types of waves. So we have a P wave comes first, and then an S wave, and then a surface wave. Here is a picture of a seismograph, and this is a vertical one. So as you can see down here, the motion is up and down. So when there's an earthquake and the ground shakes, it shakes up and down. This is a big drum of paper, and the drum rotates as the paper comes off. So picture pulling off paper towel off a paper towel roll. As the ground shakes, this drum will actually vibrate up and down. So you'll get this vibrating motion up and down. This hinge here will also vibrate up and down. Now, there's a principle in physics called the principle of inertia that basically says an object at rest will do its very best to stay at rest unless a force is applied. And the bigger the weight or the bigger the mass, the more the inertia. So this, for example, could be a 100-pound weight, and because it's so heavy, it doesn't want to move. And on that 100-pound weight, there's a little needle here, and ink comes out of the needle and draws on this paper as the paper goes up and down. So the paper goes up and down, but the mass and the ink pen does not go up and down, so it records the printed record called a seismogram. So the first type of wave that we're going to talk about is a primary wave. Primary waves can be called push waves. They can also be called compress-expand waves. They can also be called push-pull waves. And the thing with a primary wave, it's a body wave, which means that it can actually go through the body of the Earth. And believe it or not, it can go through solids, it can go through liquids, and it can go through gases. So it can really, really go through everything. It travels between 6 kilometers and 7 kilometers in 1 second in a compress-expand manner. if you were asked to draw what it actually looks like, if you were to look at this spring and imagine it being like a slinky, there's sections where it's pulled apart and there's sections where it's compressed. So there's sections where it's expanding, compressing together as the movement travels down through the spring. For a secondary wave, they are the second fastest. They are the second to arrive at a seismograph station. They travel approximately half the speed of a primary wave, and they are often called shear waves. Now, I kind of relate them, these S waves or secondary waves, to like how a snake moves. So the movement is still going this way through the spring. However, there's this back and forth motion. And it's the back and forth motion which basically reduces the speed from 7 kilometers per second down to 3.5 kilometers per second. Now, when you think about the movement of this energy through rocks involve minerals and compounds. It's pretty much impossible to shear a liquid or a gas. So a public exam item is that secondary waves, S waves, will only go through solids. What that means is they will not go through the outer core, because the outer core is believed to be a liquid. In fact, that's how we actually know the outer core is a liquid, because S waves will not go through that layer of Earth. The other type of waves are your surface waves, and they are the slowest moving waves. I was always told that they travel at about 10% slower than S waves, which is said right here. So they are the slowest of all. Some surface waves can be called long waves. I've heard of love waves. I've heard of Rayleigh waves. Essentially, they only go through solids because they go through the surface of our Earth. The biggest thing is that they're last to arrive at a seismograph station, and often too what shows up as multiple choice is that they're the most destructive. And think about it, surface waves travel on the surface, and that's where people and property exist. So most damage to humans is actually caused by the surface waves. Here's just some pictures of surface waves. Not really sure if they're long waves or love waves or Rayleigh waves in this particular case, but just kind of shows you how the motion of the Earth. In this case, you can see that the motion is more shearing sideways, like this, and in this case, the motion is more shearing up and down. Sometimes you can actually get this effect with this effect, and that's called a Rayleigh wave, so you get an up and down and a sideways shaking. So the categories of waves are surface waves and body waves. With surface waves, they're the slowest to go, they cause the most damage, really complex motion, so you can get this up and down, and you can get this sideways shear at the exact same time. So you're almost getting almost like a coil effect of movement. Your body waves are your P waves and your S waves, which we call primary waves and secondary waves. Your secondary waves are more shaking at right angles but still moving forward, and your primary waves are more push-pull, compress, expand, compress, expand. The biggest thing is that your P waves go through solids, liquids, and gases, but your secondary waves only go through solids, and this is how we know that the outer core of the Earth is a liquid, and that is your multiple choice item.